Assalamu alaikum everyone. I hope you all are doing well and taking good care of yourselves. This is your instructor Ali Faruqi and you're watching Science with Ali. So in the last class we started our discussion on energy changes, which was a brand new topic, and this is the part 2. Now, a quick recap of part 1 before we start. We discussed how chemical reactions are classified into exothermic and endothermic reactions. We also discussed how in exothermic reaction the energy is given out, and in endothermic reaction the energy is absorbed. Moving forward, we discussed how there is no reaction that exists in which there is no energy change, meaning that there is always a reaction which is endothermic or exothermic. Moving ahead, we discussed how temperature curves work, how when it is an endothermic reaction the surrounding temperature decreases, and when it is an exothermic reaction the surrounding temperature increases, how in an exothermic reaction the graph increases from room temperature and then decreases back to room temperature, and in an endothermic reaction the graph decreases from room temperature and then increases back up to room temperature. Moving forward, we then move to specific reactions that were classified as endothermic or exothermic. The first reaction that we discussed was combustion, which is an exothermic reaction. It is the burning of a substance in presence of oxygen. I gave you all the example of the stove, in which when you come near the stove, you you feel the heat coming from the stove, and the methane gas is burning, which is providing energy as a product. We then talked about respiration, in which the glucose is burned by our body to provide us with energy, which we cannot live without. This happens actively in our body at all times. We then talked about neutralization reaction. It is when an acid and an alkali react, produce salt and water, and this was also an exothermic reaction as energy is released as a product. Moving on to endothermic reactions, we started discussing photosynthesis, which is an endothermic process, how it cannot take place at night because it needs light to start the reaction. We discussed some few important aspects of photosynthesis, which is these factors as well. We then talked about decomposition reaction. It was a breakdown of a compound into simpler compounds or elements. We had ammonia here, and then it was broken down into nitrogen and hydrogen, and it was decomposed as a result. Now, in this class today, we're going to be looking at a very, very important topic regarding energy changes. You can say that it is the heartbeat of this chapter, as it has the most exam weightage regarding this chapter. It is called energy profile diagrams. Like before, we're going to be starting with exothermic reactions first. Now, what are energy profile diagrams? So let's assume that this reaction is happening. A plus B gives us C plus D. This is just a random reaction. You don't need to worry about what is A, what is B. It's just a random reaction. All right. Now we know that everything around us, the particles that are around us, have a certain amount of energy. For example, the gas in the air, oxygen gas in the air has energy. It is that energy that enables the gas to travel and make it move, right? So in a similar way, the particles of A and B have certain energy present in them at all times. We call it stored energy. Now this stored energy has a special name. We call it ER. It is energy of reactants, the combined energy of all the reactants. Now it will be this energy that will react to form C plus D, which are our products. Now the caveat is that the energy of products and the energy of the reactants will never be the same. Let's just go ahead and write down the energy of products over here so you have a better understanding. So the energy of reactants and the energy of products will never be equal. There are two possibilities. Either the energy of reactants will be more, or the energy of products will be less, or the energy of reactants will be less, or the energy of products will be more. On this basis, we will classify the reaction as endo or exo. For example, if I say that the reactants over here have energy of 2000 kilojoules. This is just a made up number, so don't worry about it. Now assume that the energy of products have an energy of 1200 kilojoules. This is the combined energy we're talking about for the products and the reactants. Alright. Now physics has taught us that energy cannot be created nor destroyed. So there's a difference of 800 kilojoules between the reactants and the products. So where did this 800 kilojoules actually go? It is this 800 kilojoules that is actually being lost to the surroundings, making it exothermic. Remember, we studied that exothermic, in which energy is released into the surroundings, making the temperature increase. Because exothermic reaction has only one requirement, which is that the energy of the reactants has to be greater than the energy of the products. This is a very, very important point that you need to remember at all costs. This is very, very important, guys, so don't miss it at all. That is it. The most important part of exothermic reactions energy profile diagrams is this point, that the energy of the reactants should be greater than the energy of the products. For here it is 2000, it is 1200, it is a difference of 800 kilojoules, which is lost to the surroundings, making it an exothermic reaction. Now if I want to represent this info on a graph, I will do as follows. Let's just make a graph over here. Okay, now if I want to plot the reactants energy over here, so we studied that the energy of the reactants is greater than energy of products, so it must be higher than the products as well. Go ahead and drop it down. This is the reactants, I'm denoting it as R, and this is the products, right? It is P. This is the energy of products and this is the energy of reactants. Now let's just say that I have A and B present over here in a beaker, and after a given amount of time, this A and B will react to produce C plus D. Now I would expect that because it's an exothermic reaction, that the energy will just gradually come down and stop at energy of products, right? No, 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 no. Why? Because the reaction will not even start if I just add A and B again and just sit there to watch the show and magically form C plus D at the end of the reaction. Now, if I explain this to you practically, I will give you an example of the stove. In the stove equation, we discussed how you only need CH4 and oxygen, right, to form energy, carbon dioxide and water. This is the reaction that happens in your everyday stove. Now, why do you think that it produces a flame? If I just open the stove and there is methane gas coming out of the stove, there is oxygen in the air, why doesn't it just magically appear the flame and just start burning? That's the point. You have to light up a spark, you have to light up the matchstick first or produce a spark from the stove to start the flame. This explains that no reaction ever starts automatically. You need to provide a separate energy to start a reaction, which is called activation energy. Now, why do we even need this? Why do we need this activation energy in the first place? Overall, this is a separate energy requirement and it is only required to activate a reaction, to start a reaction. So initially, this is a wrong curve. This is a wrong energy profile diagram. What happens first is that the activation energy, when we supply it to the reactants energy will go up first, and the activation energy, let's just say I stop providing activation energy at this point, right? Now what will happen is, which we expected in the first place, which was that the rest of the curve will come down and then end at the reactants, the energy of the products. This bump that you see over here is the activation energy that we provided. Now if I split this graph into two parts, right, and I draw two separate lines within that graph, these are the lines for the arrows. I'll explain in a second. Now these arrows will indicate what energy is being happening, what is the change in energy, what is the activation energy. So the direction of these arrows are very important. The activation energy sign is EA. So we provide activation energy over here. So let's just go ahead and write down EA over here. Now the activation energies arrow is going to point upwards, as this is the energy required to start a reaction. This is the energy that we are providing. This is not the energy of the reactants or the products, is the energy that's being additionally added in order to start the reaction. Okay? As for the second arrow, this is the actual difference in the energy of the reactants and the energy of the products, which is coming out of the system. The energy which is coming out of the system, that is the difference. So this is going to point downwards, and we call this as delta H. Now delta H stands for enthalpy change, right? The delta stands for change, and we denote this H, which is enthalpy, the difference in the reactants and products energy. Now there is a calculation involved in this, so I will go ahead and write down the equation, which is energy of products minus energy of reactants, which will give us enthalpy change. So if I calculate the enthalpy change for the reaction that we did above, which was A plus B will react to give us C plus D, the initial energy that we gave was 2000 kilojoules, and the final energy we had was 1200, and the difference was 800, right? We knew that. Now if I just input that over here, the product's energy 1200 and the reactant's energy 2000, I will going to get a value similar to this. 1200 minus 2000 is going to be minus 800. Now this minus sign is extremely important, because it is this minus sign which will indicate us that the reaction is actually exothermic. Get my point? We concluded here that the reactant's energy should be greater than the product's energy in exothermic reactions. And this graph proved that right. And the calculation now proves that right, because it has a negative sign, which means that the energy was lost to the surroundings, which means that the reaction is exothermic. So if you're given with a reaction similar to this is an example of an exothermic reaction. React to give us CO2 plus 2H2O, and the enthalpy change is written minus x kg mole. So this will indicate you that the reaction is exothermic, right? I mean, you know that it is exothermic because it is reacting with oxygen, but this is another clue for you that the reaction will be exothermic if the enthalpy change is negative, right? Now this x could be any value. I didn't write it down because it may confuse you, but the point is, if it's a negative value of the enthalpy change, then it is an exothermic reaction. Are we clear? So now that we're done with the energy profile diagrams of exothermic reactions, we will now move on to endothermic reactions. So let's just go ahead and write down the same example that we did for the first part. A plus B will give us C plus D. Now we said that in the exothermic reactions, the energy of the reactants is greater than the energy of the products, right? We said that. Now in the endothermic reaction, it is actually opposite. The reactants this time cannot form the product. They cannot even form the product unless you give them energy. So this time the reactant's energy will be less than the product's energy. Mind you, this is not the activation energy. This is the excess energy that we need to provide the reactants with in order for them to even react with themselves in the first place, to even form the products. So if we pen this down, we can say for an endothermic reaction, the energy of the reactants is always less than energy of products. Right, so having said that, let's move on to the energy profile diagrams of endothermic reactions. Alright, so we discussed that the energy of the reactants will be less than the products this time. So the products will be somewhere around here and the reactants will be somewhere around here this time. Now in this reaction we will be continue to providing energy above the product line to ensure that my reactant starts, and then after my reaction starts, I will then go ahead and move forward with moving it down to the product side. Once we reach this point, my reaction will begin and come down back to the product level. Now if I half this graph as well and make two arrows similar to the exothermic reaction, we know that the activation energy is somewhere around here because it's a hump over here, right? This is the energy that we needed to start the reaction, and this was the energy that we provided to the reactants to give them enough sufficient energy that they can even react with themselves to form the products, right? So the reaction, the energy, activation energy is going to be pointing upwards because we discussed earlier as well. And because you are increasing the reactant's energy in this part of the graph, this will also be an upwards arrow. This is our activation energy, and this is our delta H, the enthalpy change. And similar to the first part, the enthalpy change calculation is always the energy of products first and energy of reactants later. Energy of products minus energy of reactants. Now, if I provide a theoretical value to the energy of products, let's just say I have 2000 for, let's just say I have plus 600 for the energy of products, and I have plus 400 for energy of reactants. Now, if I minus them, energy of products is 600, so 600 minus 400 is going to be a plus 200. Now, in an endothermic reaction, there will be a positive sign for the enthalpy change. Similar to the exothermic reaction, there was a negative sign. Now, in the endothermic reaction, it will be a positive sign, which will indicate to us that it is an endothermic reaction. Now, if I do an example over here with you, let's just say I have calcium carbonate, it will give me calcium oxide and carbon dioxide. Now we know that this is a decomposition reaction as we studied earlier in the part 1. So if we provide heat with this, the enthalpy change is going to come positive kilojoules mole, right? Because it is an endothermic reaction, and we know that a decomposition reaction is an endothermic reaction, but this is just to indicate you that it is actually an endothermic reaction. If you get a positive value for the enthalpy change, that's a very big hint that it is an endothermic reaction and will just make your life easier. So this wraps up a very major part of this chapter of energy changes, which was our energy profile diagrams. I hope you understood very clearly, and if you have any questions, you can drop them down in the comment section down below. In the next class, we're going to be discussing the last part of energy changes. Until then, I hope you enjoyed this video, and I will see you in the next class.